Hi everyone, welcome back to Dprieto TV. I know with this coronavirus pandemic, these are difficult times. So, since a lot of schools are out and not a lot of people are learning a lot of things, I was thinking that I could bring my knowledge of science because I love science. It's a beautiful thing to study. So, I was thinking I could bring my knowledge of science to you guys and, well, teach you guys about science. So, basically what I'm going to do, this, as you saw in the title, this is Season 1, Episode 1. So basically today, each day I'm going to do lessons based on like different topics. So today you saw is the basics of chemistry. So that's what today's episode will be about. So I don't think there's any other aspects. So let's get started. Okay, so everyone, this is where we'll be doing our lessons. So as you see, today's lesson is the basics of chemistry. Okay, so what I'm going to try to do, I'm going to try to make this as simple as possible to help you as viewers understand, because some of these things that I know are a little too complex, so I'm going to try to make it as simple and understanding for you. So we won't go into stuff like super hard stuff. I'm going to try to keep it like understandable level for you guys. So, so today we see our key terms. We have solid, liquid, gas, plasma, melting/boiling point, Brownian motion, element, compound, mixture, and the glorious periodic table. So let's start with solid. So that fell. Okay, so a solid is okay, let me write over here. So see, you guys see me in the camera. So a solid is there's three main points of a solid. So a solid is the lowest energy state. So it has the lowest energy out of all the states of matter. I'm pretty sure you guys probably know some examples of solids, like you. You are a solid. Everything on this table is a solid except for my water bottle here. Okay, and another thing. So another critical aspect of solids, it has a fixed volume. What I mean by fixed volume is it has volume. Like every solid, like if you're in math, you have to measure like how much space something takes up, right? It's a volume. So all solids have fixed volume. Okay, another critical aspect of solids is slow atoms. So atoms inside a solid are very slow. So you can see my model atom here. You can see off the camera. Can you see it? Yeah. Yep. There's my atom thingy. So this thing is going to be representing. So the atoms inside every solid that we know are very slow. They move. They're not incredibly fast, unlike gases, which have very fast electrons. These atoms move very slowly. Okay, so let me just scroll to the next point. Okay, so another. Speaking of volume as well, solids also resist a change in volume unless you liquefy them. Also, atoms inside solids have a crystal structure. So, and hence diamonds. Diamonds have a crystal structure. Another solid. Plastic has a crystal structure inside, but I won't get too much into that. Okay, now let's go to the next key term and look at that. Also, I forgot to mention, at the end of every class, I'm going to try to do something that you guys can do at home. I'm going to do like an experiment of the day, so I'm going to try to make it interactive for you guys. So the next term that we're going to be talking about is liquids. Liquids have, like solid, they have three main aspects. Liquids have they kind of have a fixed shape and volume. So liquids basically, they fill up any container that you put them in, and you can change their volume by putting them in any container. Okay, so another aspect, like the what's it called? Solids. They have medium state. So they're like the state in between solids and gases. So they're like that They're like that kind of solid, kind of gas. So they're like that bar line. Okay, another point about liquids, like I said, is they have medium speed atoms. So let's take our little model atom again. So this little model atom, it doesn't move incredibly fast, but it's, like I said, it's like liquid is basically like the middle line of all the states of matter. They have like all the middle line characteristics. So an atom would move like slowly like that, and you're able to fix its shape. And an example of a liquid is water. Probably the most important liquid of them all. Okay, so another thing about liquid, if you want a little more complex stuff, when there's attraction between liquid, that is called surface tension. If you haven't heard it, you can see the term up here. Where is it? Okay, so you could, if you heat up a liquid, you'll decrease the pressure of the liquid as well. And then you'll decrease the pressure. Okay, so also this is another like complex thing that you could know. So if there's some liquids that can dissolve solids like acid, some acids can burn right through like concrete. Those liquids are called solvents. Okay, so now the next term, we've covered solid and liquid. The next term is gas. Very, very interesting state of matter. Okay, so the characteristics we have identified in solid and liquid, this has no fixed volume. It'll never have fixed volume, and it will never have it in the history of the universe. It's just ready to run free whenever it wants to. And then, okay, next characteristic, fast. We should put very in parentheses. Atoms. Okay. So the atoms, let's go to our model atom again. The atoms move incredibly fast, the hotter it gets. So heat has to play a special role in this. So when you heat up an atom, it gets faster and faster and faster and faster and faster and faster. And that's what makes these states change. And that's when we're getting to melting point later. Okay, it is also the highest energy. This is the state of matter with the highest energy. So some examples of gases are, if you look around you, you're surrounded by gas. Air. Air is a gas. Okay, and some other little like non-essential things that you don't need to know is that it's usually invisible. Gases are usually invisible. Well, if you have chlorine gas, it's really, really toxic. It has like a pale green color. Iodine gas. Iodine is an element where it has a very low boiling point around 102 Fahrenheit. It's around 102 Fahrenheit. So when you burn it, well, I just dropped my marker. So when you burn it, it turns into like a vibrant pink gas. That's pretty cool, but you still shouldn't breathe it. So this is not the same for gas. This is the same for anyone. So when gas is exerting a force, that can also be felt as pressure. Hence the air pressure. All the air pressure from the atmosphere is just pressing on you, and that can be felt as well, air pressure. Okay, so the next state of matter, there's actually one above gas, but it's not common. Well, if you set something on fire every day, then yeah, it's common. The state of matter is called plasma. Plasma is basically just like a step above gas, so it's basically ionized. So ionized, you'll learn that in next week's episode when we discover the parts of atoms and like the subatomic particles. So if you're wondering about an example of ionized gas, fire. Fire is plasma. Fire is basically just ionized gas. That's basically what it is. Okay, so the next terms, we covered all the states of matter, and there's one below solid, but that's a lab-made matter. I won't get into that. That's bogus numbers, which is too complex for you guys. So we're going to be talking about, I'm going to do this in separate parts. So first, melting points. So the melting point is when, let me see my notes, when a solid, so I'm going to put a diagram here. So a solid That's going to represent our solids. So actually, let me just do a key to begin with. So solids, I'm going to represent them with a square. So this is a solid. I'm going to drop. That's my drop. It's not the best drop. That's going to represent liquid. And then gases, I'll represent them by like a sphere. Yes. So that's going to represent our stuff. So melting point is when a solid goes into a liquid. So basically the melting point is a measure of how easily forces, like the heat forces, how easily forces inside solids are broken. So when you heat up a solid, the atoms vibrate. So like I said earlier, the atoms, when you heat them up, they vibrate more and more and more. So they get really, really hot, and then they're able to melt the solid. Okay, so our next point that we will talk about is the boiling point. This is kind of like the melting point. So it's like a transition between different states of matter. So the boiling point in all elements and materials is when a liquid turns into a gas. Okay, so it's basically, like I said, it's basically a measure of how the forces inside liquid are destroyed. So the process is the intermolecular forces ripping apart the atoms and basically turning into a gas. But I won't go into like forces until we get to physics, which is in about 4 episodes. So basically, like I said, your little atom is heated up, and then it basically, like the forces of it just moving around, so that just rip the liquid's molecules apart and then basically turn them into a gas because there's so much heat. There's some other points that I won't get into. So like when a gas turns into a liquid, you might have heard this term, condensation. That is when a gas turns into a liquid. Liquid, I'm just going to represent that by a triangle now. When a liquid turns into a solid, that is a freezing point. Some other ones are when this is one that not many know. This is when a solid doesn't stop at liquid, it goes directly to a gas. That is called sublimation. An example of that is, if you've ever seen dry ice, it's a solid, right? It's frozen carbon dioxide. And you see it like expelling gas all over the place. That is sublimation. That is a solid going directly to a gas. Okay, so the next term that we're going to discuss, it's a little more complex, but I'm going to try to simplify it to you. It is called, Brownian motion. Okay. So basically what this is it's basically a description on how particles move around in liquids and gases, not solids, only liquids and gases. So I'm going to try to explain this. So as you see here, this is actually coming out from a real story with the guy who invented this. I forgot what his name was. I'm just going to call him Mr. Brown for now. So what he did, so when he was examining pollen under a microscope, he just saw it moving all of a sudden, like it just started fidgeting. And then Albert Einstein, and then later, like probably like 150 years later, Albert Einstein's like, it is moving because of Brownian motion. All the molecules inside, like I've been saying, the molecules, as you see my little atom guy here, they're moving around. They're basically like bumping into the sides and making the liquid or gas move. So that's how the liquids and gases can move in real life. Also, that has to do with inertia and forces and all that stuff, but we'll get to that later. Okay, so the next term is elements. There are, I think we're going to discuss 3 things you should know about elements. 1, they are the building blocks of the universe. They're the building blocks of the universe. Every single solid, liquid, and gas that you see, except for the non-artificial ones, which we'll get to later. Every single solid, liquid, and gas you see has one of these elements. And it's not just one element out there. There are 118 elements known to man, which only 92 of them occur naturally. Okay. So as elements get heavier and heavier and heavier, they go in like this order. So first we have the first element is, just move it over here if we need to move the camera. So the first element is hydrogen, represented with an H. So hydrogen has, let me see my notes really quick. Has one proton, so one proton, and protons are always represented with a P, and a plus sign next to it, and then one electron. And electrons have a negative charge, which we'll get to next class. So they have a negative charge, so they have an E, so they have a minus right next to them. So helium is number 1. Helium is the lightest thing in the universe, and it's the most abundant thing in the universe as well. Helium is He, that's the chemical symbol. So helium has 2 protons and 2 neutrons. Neutrons have no charge at all. They're neutral. And the electrons vary from element to element. So as you see here, we can basically like predict how elements will change. So like the next element is lithium. If you've heard of lithium-ion batteries, this is element number 3. It has 3 protons and I think some number of electrons, but we'll get to that later. Okay, so if you see on the periodic table, I'm just going to do hydrogen for example. So the characteristics of an element can vary. So hydrogen, if you always look at a square on the periodic table, which we'll get to later, the number up here in the corner is the atomic number. The atomic number is, like I said, hydrogen is the first one proton. The atomic number is the number of protons in the nucleus. And then there's some words down here. Usually the words down here is the name of the element. So hydrogen, that's number 1. Usually they have like an ionic charge, but I won't get into that. I don't know the ionic charge of some elements. And then up here in the corner, which I think is yes, right here is the, I'm just gonna put some, I think it's 1.00139. That is the atomic mass. The atomic mass is the nucleus. So if you know, the nucleus of an atom is the protons and the neutrons, not the electrons. The electrons, so if you see here, the electrons pretend some electrons. So the electrons orbit the atoms. So the atomic mass, it's a very different scale. It's not kilograms or pounds. It's a very different scale. I think it's called mole. It's called mole, like a mole, M-O-L-E. It's not the animal. Let me see here. So mole, it's a chemical. It's a way to measure atoms. So I'm not going to get into that. So don't worry about that. So that's basically what the atomic mass is. Okay. So now term number 8 is compounds. Oh, you can't really see that. Let me erase this. Okay. I think you'll be able to see it now. So I don't know why you're still not able to see this. Okay. So compound. So compounds. Look at my notes here. Compounds are, let's not down my water. So compounds, they are a combination of different elements. They are a combination of different elements. So compounds, they can be destroyed and they can be made by chemical reactions. So give a good example. They like to form, there's 2 types of compounds. There's ionic compounds and covalent compounds. An example of an ionic compound is salt. Salt is an ionic compound. I think we're going to get to like ions on the next video. So next class. An example of a covalent compound is water again. So compounds, like I said, Salt, if you know, is sodium chloride. That's a combination of two different elements. And water is hydrogen and oxygen. So compounds, like I said, are a combination of different elements. Okay, so the next term is mixture. Mixture. And if you think they're like compounds, you are wrong. Compounds and mixtures are very different things. Mixtures are two substances mixed together. So a good example for a mixture is they can be separated by physical means. So and they cannot be made by chemical reactions. So an example of a mixture, I have this little bag of. So this is like I saw it in a book. This book called Chemistry by Basher, and I'll have a link down in the description if you are thinking about buying it. So a mixture is like a good example. A bag of, this book says a bag of marbles. It's a really good example of a mixture because they're not fused together like you see. Let me just pull out two marbles. So I have a red and an orange marble. So you can't, like compounds would fuse them together, so they would be red and orange. That's like light red. This is a dark red. And mixtures just put them together. They don't fuse them together. They don't fuse them. They just side by side. And then what I mean by physical means is like, for example, this is your mixture. You can take out, like, for example, you can take out a yellow. You can take out a red. That fell. You can take out a red one. You can take out multiple. So basically, that's what a mixture is. Okay, so the last term that we were talking about today, and it's my favorite term, is the periodic table. One of my favorite topics to talk about in science. So just get my notes. So I say, well, most scientists outside the world say it is one of the most important discoveries of all time. I'm just going to put a clock here. Okay, there's all time. So basically, the periodic table, it's basically a chart, as you can see here in my periodic table here. It's basically a chart to organize all the elements, all 119, into like different categories. So as you see, the vertical lines here, they are called groups, and the vertical ones, yeah, they're called groups. The horizontal lines, like one here, one here, one here. These two top here, that is considered one line. Those are called periods. So these are categorized into like different categories depending on their reactivity, use. Basically, they're categorized on that. And like I said, they move on from left to right based on their atomic number, which we learned is the number of protons in the nucleus of the atom. So basically, I'm gonna like tell you what their uses are and what the categories. So the first category, I'm just gonna remove this here. Let me see if I can spell it. Is alkali metals. These metals are very notorious for blowing up. So basically these metals, lithium, sodium, potassium, rubidium, cesium, and francium, they all react with water and air. So usually they usually just start fizzing and then they catch on fire and then they blow up. That's basically how the alkali metals work. And an alkali metal example that I'm pretty sure you have in your home is a lithium-ion battery here. You can see here this lithium-ion battery. It contains lithium, which here is element number 3. And it's actually it's the softest metal of them all. So that's basically what's in the lithium-ion battery. Okay. So let's move on to the next category, which is alkaline. Now alkaline alkaline earth metals. These metals, they kind of react like the alkaline metals, except except instead of like blowing up, they release they ignite and they release colors like magnesium. Magnesium here. If you heard of magnesium, it's infamous for when you burn it, it's infamous for sending off bright white flames everywhere, and it's very bright. You should not look at it. What's another one that you probably guys know here? Calcium. Calcium is also very flammable as well. It's a metal, if you did not know that. It's used for building parts of the body, like the bones and the teeth. So basically, yeah, that's basically what they're for. I thought I had an example here. Okay, so let me just take my notes. Okay, so let's move on to the next category. Okay, so category number 3, okay, is the Great Transition metals. These metals, this little group here, these metals are used in industry a lot. So as you see here, I have some examples of the alkaline metals. As you can see here, I have of the transition metals. I have here the lock. You can see on the camera the lock here. I just have scrap metal. These are probably using the transition metals. Some common ones that you guys probably know is titanium, iron, copper, zinc, silver, gold. Gold is on there. Some of these elements are really toxic, like mercury. I'm pretty sure you guys know mercury. And cadmium. I don't know if you guys know what cadmium is. It distorts the muscle in the brain and it just kills you over time. It's another one you guys probably know. Tungsten. I don't know if you guys know that's used in incandescent light bulbs because it is the toughest element around. It doesn't melt until 3,000 Celsius, which is about 8,000 Fahrenheit about. So yeah, let's move on to the next element category. So category number 4 is Category number 4 is the poor metals. The poor metals, they include this little triangle right here, this little wedge here. They are the poor metals. Some poor metals that you know, lead. What's another one? Tin. Tin and lead. Tin is used in tin can. Lead. Gallium. Gallium has a melting point of around 85 degrees Fahrenheit, its melting point, its freezing point is 85 degrees Fahrenheit, but if it's hotter and you bring it down to 85, it'll melt. So basically, these guys have a better electroconductivity, and they're kind of like transition metals along with the lanthanides, which I'll talk about later. So these guys, basically what they do is they have a lower boiling point than other metals, like this one, gallium, I said it's 85 degrees Fahrenheit. So basically they have a lower boiling point and higher electrical conductivity. Okay, let's move on to the next one. The next one is it is the non-metals. The non-metals include elements like nitrogen, oxygen, phosphorus, sulfur, basically, and also selenium. Those are non-metals. Well, I'm pretty sure you know what non-metals are. They don't have metal. Also, hydrogen fits into that category as well. They are good for electrical insulators, which we will get to electricity and magnetism later in this classes. So basically, electrical insulators, they stop electricity, and we will get into conductors and insulators later. We will get into conductors and insulators level. There are two types of nonmetals. There's polyatomic and diatomic, which I won't get into because that's more complex stuff. So the one, as you see, we've covered the elements here in this triangle and here, but we never covered the elements that go right in between right there. You see this little line? and it covers the elements that go there. Those are called the, that's not spelled metal. They are metals, fun fact. Metalloids. They're metalloids. So I also call them the semiconductors. Semiconductors. So basically what these guys are good for is, oh, I forgot to show you an example. So this is an example of a poor metal, aluminum. Aluminum is a poor metal, so that's one example. So the semiconductors are really, really good for using in electronics. Here's my Arduino board. You can look at my Arduino video. So this Arduino board usually uses elements like silicon and germanium. Those are very highly used electronic pieces, and they're widely used in and those are widely listed in the metalloids. Okay, so the next category is one of my favorite categories of them all. Is this next category is the halogen. Oh gosh, I can't spell. Let's do that again. What's this one? Halogens. These are the halogens. This line right here, all of those elements are the halogens. These guys like to react with anything they can find. Anything. Fluorine is considered the most reactive element on the periodic table. It can react with plastic, other elements, it reacts probably with every single other. It can even break, it can react with glass, which is basically very dull. So basically these guys are very reactive and sometimes very toxic and poisonous, like this one, and this one. Well, basically all of them are toxic and poisonous, so don't eat them. Okay, the next category is another good category to talk about as well. It is the noble gases. Also an example of halogens. You probably have a halogen in your room. Toothpaste. Toothpaste uses fluorine or fluoride, so it uses fluorine, which is one of the elements in the halogens, which is very, very, very reactive. So, noble gases. Noble gases. They are all gases except for this one. This is an element that I'll get to later. These elements don't react with anything. They will never react with anything you find. And when you run electricity, so if you have some in like a tube, when you run electricity through them, they make bright colors. So an example here would be my plasma lamp, if you just turn the camera over here. My plasma lamp has noble gases inside, and that's how you can see the colors through the lamp. That's how, like I said, when you run electricity from noble gases, they excite and they make cool colors. Okay, so the next category is category number 9. We just finished talking about the noble gases. So next is the lanthanides. These guys, they're not super special. They're basically transition metals, but they're located at the bottom of the table. They have weird names, and they're used in a lot of like electronic parts, like TVs and phones and like MRIs. Most of these elements are used in MRIs. So they're kind of like the metalloids or / semiconductors. So one they're really good here. So one of these parts in here, I think that little metal part with the disc around it is made of one of these elements. I think terbium. Terbium is made out of. And also another element that you may have heard of that's on here is neodymium. Neodymium magnets, they make some of the strongest magnets in the world. Okay, so the category below it, which I do not have an example for it, you'll see why. The next element category, is the actinides. These elements at the bottom, this bottom row. All these elements, every single one of these elements is radioactive. No matter what, and up to uranium, which I'm pretty sure you guys know what that is. So this one, They're the last naturally occurring elements in the world. All the other ones from beyond, so element 92 and above, element 93 and above, those are all artificial elements. You can't find them in real life. Some people say that they don't have any uses. They have I think there's one element with one use. It's called americium, which is named after America. It is used in smoke detectors. It's like a tiny little cube of it, but it's very shielded so you don't get radiation poisoning. So yeah, it's basically used in smoke detectors. Okay, last and not least category is, I'm not going to cover too much on this because it's very short, so the unknown. The unknown kind of sounds like, ooh, it's very weird. These elements, like the elements above 103 and above, they have no use. They have very short lives, and they're not a solid, liquid, or gas. The people who have made them, like Berkeley University of California, they only made like an atom of it, and they last only for like 20 seconds. So they don't have any use besides just scientific discoveries. Okay, so I think we finished covering the key terms for today. So now we will get into the experiment of the day. So let's get started. Okay, so this is the experiment of the day. So each class, at the end of the day, I'm going to show you guys an experiment that you guys can do at home. So today's experiment of the day is from this book called The Big Book of Science Experiments. I put a link down in the description, so if you want to purchase it, it's right there. Okay, so we are going to go to physical science. Let me just find it real quick. Page 95. Here we go. So I'm pretty sure you guys have done this at home, so let's get started. So what you need vinegar, salt, a timer, a teaspoon, a bowl, and some tarnished pennies. By tarnished, I mean they kind of look like dirty and stuff. Like if you see this penny here, it's a little dirty compared to this penny right here, which is nice and shiny. So this has to do with chemical reactions. So the experiment of the day that we'll probably do is probably going to be related to what we learned today in the class. So macro, let me just get it. Oh boy, where did it go? Here we go. Okay, so first direction that to do. So you just move all this here. Fill the bowl 1/4 full with vinegar. So I'm just gonna pour this vinegar here. That's about 1/4, right?
Yeah.
Okay. So the next, add 1 teaspoon or 5 milliliters of salt. So I'm just gonna take this over here. Add a teaspoon of that. That's about a teaspoon, right? It's about a teaspoon.
It's about a teaspoon. It's not a teaspoon.
What is it about? That looks like a teaspoon.
That's less than a teaspoon, but go for it.
Okay, so that goes in there. That goes in the mix. So
do you get
add
something
the
to
pennies.
mix it?
Yeah. Let me just mix it up with the end of this. You can clean this part later. I'm just gonna put it on.
You didn't mix the salt in. It's on the bottom.
You can mix this a little more.
It's still.
Okay, let's just not mix it for now. So let's leave it like that.
It seriously smells.
Okay, so step 3, add the pennies. So you take some tarnished pennies, like I said, dirty pennies, and you add them in.
Oh my God.
And now we set a timer for 5 minutes, and we wait for 5 minutes. Okay, so 5 minutes are up, so let me just reset this. And the pennies look different now. So let me just wipe it with the... I'm going to close it so I don't spill any vinegar. So let me just clean this up. And there you go. Shiny penny again. Let's just pull out this one. This one looks a little dirtier. But I think once I wash the grime off of it, it'll look shiny again. So hopefully it'll look shiny again.
Just keep scrubbing.
It's a little shinier. I think I needed to put it in a little longer than the 5 minutes it said. This one looks shiny again. And so does this one. Okay, so you might be wondering what is happening. So what is happening? A chemical reaction is taking place. So when the penny gets dirty, it has like a green color, brown, black, green color to it. That's because it's reacting with the oxygen in the atmosphere to get all dirty and stuff. So when you put it in a liquid, like we discussed today in our class, so when you put it inside a liquid, when you combine vinegar, which is an acid, which we'll learn about later, when you have an acid, and then when you have the vinegar acid, and then you add it with salt, you actually create an acid called hydrochloric acid, which is the same acid in your stomach. Fun fact. So basically what happens, the acid takes away the oxide layer because it's all dirty from the oxide layer. So the acid takes it away and you're left with basically shiny pennies. So basically that's how our classes are gonna work now. So we are gonna have this every other day. So next week we're gonna do a challenge that you'll have to see. So subscribe and find out. Then the week after that we will be discussing season 1, episode 2. Basically we're gonna be talking about the parts of atoms. So basically like atoms, protons, neutrons, electrons, ions. I've mentioned ion a lot today. So next class you'll learn more about ions. So if you want me to, I'm also starting to run out of ideas for videos. So if you want me to use your ideas for videos, comment down below your ideas.
Or you could ask me.
Or you could ask my sister, who's right behind me filming. So thank you for watching. Like, share, and subscribe. Get this video to the front page, and I'll see you later. Hi everyone, welcome back to Dprieto TV, and welcome to the new episode of Prietology. So what I'm going to try to do in this series is transfer my knowledge of science to you guys and trying to make it in the simplest way possible. So what I'm going to do is these episodes of Prietology will be every other video. So this video is Prietology, and then the next video will be a challenge video, and then the video after that will be Prietology. So if you watched the latest episode, you would have learned that we talked about the basics of chemistry and the states of matter and melting points and boiling points. Today we are going to take that with a little further, so let's get started. Okay, so as I said, this is a new episode of Prietology. The title today is The Building Blocks, like I said. So today's episode, we're going to be talking about basically what elements are made of, so like atoms, protons, neutrons, molecules. So we have our key terms like last class. So we have atom, isotope, ion, molecule, polymer, metallic bonding, nanoparticles, Avogadro's number, and mole. Okay, so we shall start with atoms. So atoms, they are the building block of element. There are 118 known elements, which means there are 118 known atoms. So atoms are made of protons, which is always represented with a P with a plus sign, neutrons, which are represented by a N, and electrons, which are represented by an E with a little negative sign. Protons are positively charged, and neutrons are neutral charge. They have no charge, and electrons have negative charge. So electrons orbit the atom. So let me get my model atom. If you remember my model atom from last one. Protons, I'll draw helium atom. So helium, 2 protons, 2 neutrons. So these are my protons, these are my neutrons. And what I mean by energy shells is the orbit that electrons take. So here's an electron. So electrons always orbit. So they have different shells. So like, as I said last time, the periodic table is organized into rows and columns. So when you go by each row the shells get bigger. So in the next row there'd be 2 shells. So with another electron, so another electrons, and then a 3rd shell, then a 4th, and a 5th, and then it just keeps going and going and going. Okay. And then I think I briefly mentioned atomic number last class. The atomic number of an atom is based on the number of protons in the nucleus. So if there are 2 protons, it's element number 2. If there's 3 protons, element number 3. You get it. And also, this is just a little fun fact. The number of protons is always equal. It will always equal the number of electrons. So if there's 6 protons in the nucleus of the atom, there would be 6 electrons on the outer shell. So the mass number equal to the number of protons and neutrons. So if the nucleus of the atom has 6 protons and 2 neutrons, it would be 6 plus 2 is 8, so the mass number would be 8. Okay, so now that we discussed atoms, there's another part of atom. This is, for me, is like the evil twin brother of atoms. It is called isotopes. Isotopes are atoms with same atomic number, but with different mass numbers. Okay, so this might sound confusing, but basically they're atoms that contain equal number of protons, and then the neutrons, they have a different number of neutrons. So it has 1 neutron, and then it still has 2 electrons. So they still have 2 electrons. So that would be an isotope. So isotopes that decay are called radioisotopes because of radioactivity, which we will discuss in another season. So an example of an isotope, I'm pretty sure if you've heard this one, it's called carbon-14, which is written like that. Carbon-14 is used for carbon dating, which is for like figuring out the age of the Earth and the age of fossils, and that's pretty much one of the main primary uses of radioisotopes. Okay, so we discussed atoms and we discussed isotopes, but wait, there's another part of atoms called ions. The ions are atoms that have gained or lost an electron. So basically, I mentioned atoms a lot in last week's episode. So ions, so let's say we have our atom here, so we have protons, neutron, and 2 electrons. Okay, so ions are held together by electrostatic forces. We'll get into electricity later in this series. So ions transfer electrons to outer shells of atoms. So let's say this is the outer shell of my atom, and there's 1 electron here. Ions would be able to transfer this electron to here. So, and then they would fill up the shells while they're full. So they would transfer electrons basically to or from the outer shells of atoms to make them up. And this makes them positive and negatively charged ions. And ions can make ionic compounds. We talked about ionic compounds last time. An example of an ionic compound, salt. Salt's a perfectly good example of an ionic compound. So ionic compounds usually have high melting points and also boiling points. Okay, so now that we discussed the 3 types of atoms, atom, isotope, and ion, we are going to talk about what brings them all together, and that is molecule. So molecules are 2 or more atoms held together by covalent bonds. If you remember what covalent is, covalent compounds, we learned about that last class. So in the terms of nonmetals, it lets 2 nonmetals combine, and then they create electrically neutral and stable substances. And it also lets nonmetal atoms to cooperate in filling the electron shells, which I've mentioned a lot, which is the shells around the atoms, electron there. And also the bonds between atoms are strong, while the intermolecular, so like a molecule, an example, H2O. So we have our hydrogen, and then we have 2 hydrogens and an oxygen. That bonds between the atoms, so if I have another hydrogen, I have another water atom, these are very strong, but the bonds between the molecules themselves are very weak. This might seem a little confusing, but all compounds are molecules, but not all molecules are compounds. A compound, like we learned last class, is 2 elements fused together to create a new substance. So water, for example, is a compound. But what I mean is not all molecules are compounds. An example of a molecule is hydrogen gas. This is hydrogen gas. So hydrogen gas, it's not a compound. It's not a compound because it's not 2 different things. It's one molecule. and it is not a compound. Okay, so now that we've talked about molecules, there's a different type of molecule. It's called a giant molecule. Those are molecules with a lot of bonds. And a really good example of a giant molecule is polymer. A polymer is a giant molecule that has many useful forms. A molecule that has very useful forms. So basically, a polymer is a bunch of repeating hydrocarbon molecules. And if you don't know what hydrocarbon is, they're molecules with basically like skeletons of hydrogen and oxygen. An example of a hydrocarbon would be water. So examples of hydrocarbon, examples of polymers that you probably know is one, plastic. Plastic is an example. PVC is an example. Rubber, as in this rubber. And also another key characteristic about polymers, they are very flexible. You can manipulate their shape while they're in solid. So like rubber, you can manipulate their shape because they're a polymer. Okay, so our next term is metallic bonding. This can get a little complex, but I'm going to try to simplify it. So basically metallic bonding, it's one of the three types of bondings. The other ones are ionic and covalent. So metallic bonding is the reason why metals behave like metals. So basically if a metal is superconductive, it's because of the metallic bonding. If a metal has a high melting point, it's because of covalent bonding. So like I said, the properties of the metal depend on the way the metallic bonding. So the metals during metallic bonding, they're held together in a lattice of positive ions. An example of a lattice, if you don't know what a lattice is a badminton racket is a good example. As you can see here, this is like a lattice is basically like this square checkerboard kind of pattern. So basically, they're made in a lattice of positive ions. So let's put some ions like that. And they're held together with the bond, so they're basically held together like that with C's, as you say. Most people say C's with C's of electrons, C's of electrons. And metals are usually held together by electrostatic forces like ions. Okay, so our next term is the nanoparticles. Nanoparticles are, nanoscopic particles. And if you don't know what a nanometer is, 1 nanometer is equal to 1 billionth of a meter. So a nanoparticles usually range in size about from 1 to 10 nanometers. So basically they're little tiny little particles that have, as I say, cool properties. They're able to change a substance completely different. So basically silver naturally can kill like germs and bacteria. But if you add nanos and then it creates nanosilver, it can create superbugs. It can kill superbugs that can basically wipe out the entire planet. And zinc oxide nanos absorb UV light. An example where you can find nanoparticles is in sunscreen. This is zinc oxide. These usually have nanoscopic particles which can block and absorb UV light so you don't get sunburned. Okay, so the next term that we're going to talk about, these last terms, Avogadro's number and mole, they're related in very specific ways, but we'll start with Avogadro's number. So the number is named after some guy named Amedeo Avogadro. Yeah, that's how you say it. So Avogadro's number is a number that says, so it's a number that says how many moles, not the animal. So like I think I briefly mentioned moles last lesson. Moles are basically it's a chemistry unit of measurement. So RAR and a molecule of gas. It usually works with gases, and this special number is 6022 followed by 20 zeros. So I'm not gonna write all the zeros. So 6022 followed by 20 zeros. And the number equals, the Avogadro's number, it always equals the number of particles in 1 mole of substance. And we'll get to mole right now. Okay, so our next term is mole. Mole is a chemical unit of measurement. So 1 mole is represented with just lowercase lowercase m-o-l. 1 mole is equal, I don't think you need to know this number, but this is, 1 mole is the Avogadro's number. If you want the Avogadro's number simplified down, it's 6.02 times 10 to the power of 23. So 1 mole beta element or compound always contains the same number of atoms or molecules given an Avogadro's number. It's a little complex, but what I'm trying to say is the weight of each mole, which is the Avogadro's number, is equal to the atomic mass of each element measured in grams. So I'm going to try to simplify this to understand. So 1 mole of, let's say, elemental oxygen, so just O, equals 16 grams. And then 1 mole of gaseous oxygen, which is O2, equals, since it's 16 grams, it would be 16 times 2, because there's a little 2 here, so 16 times 2, which equals 32 grams. So 1 mole of gaseous oxygen would equal 32 grams. Well, I think we covered all the terms for today, so let's get on to experiment of the day. Okay everyone, this is experiment of the day. So today's experiment is seeing how water molecules, as we learned today what molecules are, react with heat. I mentioned heat a lot last class. So basically what heat does, it can melt solids, it can melt liquids. So heat is basically responsible for making the different states of matter change. So this experiment is great for testing how hot water molecules can react with cold water. So basically what you need 2 clear glasses, 1 filled with hot, 1 filled with cold. I'm gonna go fill them up really quick, and some food coloring. Okay, so I am back with the glasses. This one is the hot water, this one is the cold water. So basically what you have to do is I put the blue is gonna be for cold and the red is gonna be for hot. So I'm gonna put 1 in each. So if we could bring the camera down, so I think we could get a better look at it. So we're gonna put, this is the red water first. So no, I think the instructions just say to drop it in. So let's put in a drop and see what happens. As you see, it goes down very, 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 very fast. And all the heat, as most people say, heat rises. So you can see the color rising very fast to the top. Now let's try the blue, which is our cold water. So let's put it in. Put like 1 drop. I think 1 drop would be good. Come on. As you see, it falls down much, much more slowly. And you see the color is most of the color is starting to sink to the bottom. Some of it's going up because of buoyancy. So basically what's happening is the colder molecules, the food coloring spreads faster more in the hot water than the cold one. So since, like I said, when there's heat applied to atoms, they move faster and faster and faster until they can form different states of matter. So basically what's happening is that the hot water molecules move at a faster rate, and the cold water molecules move at a slower rate because they're colder. So basically this is how our classes are going to work. So like I said, every other day, few terms, defining them, explaining what they are. So our next class is going to be about acids and bases. I'm excited for that one. So thank you for watching. Like, share, and subscribe. Get this video to the front page, and I'll see you later. Hi everyone, welcome back to Dprieto TV and welcome to the new episode of Prietology. So if you remember from our last episode, we talked about the basics of elements like atoms, molecules, ions, isotopes. Today we're going to take that a little step further and going more into chemicals and what makes them different. So today's lesson is about acids and bases. Okay, so as you see today, we only have 4 key terms. We have acid, base, pH, and universal indicator. So, like I said, also today we will be talking about acids and bases, so let's start with acid. Okay, so our first term is acid. Acids are chemicals with a low pH. We're going to talk about pH later. And usually acids are a donor of positive hydrogen ions. We learned what ions are last time. So when you put an acid like, let me give you an example. Vinegar. Vinegar is a really good example of an acid. Also, Lemon juice. Lemon juice is a good example of an acid as well. These contain lemon juice, which is an acid. So when you put them in water, they disassociate and breaks into the acid. The acid breaks the water into positive hydrogen ions and positive hydrogen ions and negative hydroxide ions. I'll talk about what those are later. And when associated with the pH scale, they are 0 to 7 on the pH scale, which usually is involved with universal indicators. So usually acids that are weak are very corrosive. An example of a weak and corrosive acid is methane acid, and usually strong acids are sometimes mild. An example of a strong acid is carborane superacid. Usually weaker acids are higher near the 7 range, and stronger acids are usually near the 0 range. Okay, so our next key term is base. Bases and acids are like polar opposites. They're completely different. Bases, unlike acids, have a high pH. Acids have a low pH. And also, bases are donors of negative hydroxide ions, which are just negative and then OH ion. And then while acids are donors of positive hydrogen ions. And usually the most common bases are called alkalis. Bases usually make up the alkali metals and alkaline metals, which you discussed in the first episode of Prietology. And the third thing is that there are 7 to 14 on the pH scale, so they're the higher half of the pH scale. Acids are the lower half of the pH scale. One of the strongest base I think out there is sodium hydroxide. They have the ability to melt fat and unclog drains. And I'm not sure about the weakest base out there, but the weakest base out there, one of the weakest ones is ammonia. I'm pretty sure you've heard of ammonia. Ammonia is used in metal cleaners like this. This contains ammonia, right? Yes. And another example of a base that you probably have in your house is soap. Soap is a really good example of a base. It's probably all around your house. Okay, so the next term... Who is this?
Hi, I'm secretly tuning into your lesson because I hacked your network.
Oh, okay. Well, why would you do that? That's just my only question.
I called you because I have a question from your lesson.
Okay, well, what's your question?
Okay, so the question is, how are acids and bases related?
Okay, well, that's actually a really good question. Let me explain. Well, as you guys heard, this hacker guy asked, how are acids and bases related? So basically, it all starts with water. I'm going to draw my cartoony water molecules here. I'm sorry that I wasn't able to get my model atom because we didn't need them for today. Okay, so like I said, positive water molecules. So when acids like to give away the positive hydrogen ions, and the bases like to give away the negative hydroxide ion. So positive hydrogen, like when it's an ion, is also positive here. And when it's negative, it's negative OH, hydroxide, hydrogen. So acids and bases, when you put if you put one in water, so let's say you put an acid in water or a base in water, the acids are going to take away the hydrogen, and the bases are going to take away the hydrogen, and the acids are going to take away the hydroxide. So this would belong to the bases and this would belong to the acids. As we learned last time, ions are molecules that have gained or lost an electron. So since these have lost one, since these are losing their electron, they become ionized. And somehow they would probably combine back because, well, opposites attract because of electricity. So like I said, the acids take the negative hydroxide and the bases take the positive hydrogen.
Oh, great, thanks. Also, you wouldn't mind telling me your social security number, would you?
Well, of course not.
Are you sure?
I'm positive.
Are you absolutely...
Some people are a bother. Okay, so our next term before I got interrupted, our next term is pH. pH measures how acidic or how many positive hydrogen ions there are in a chemical. So, like I said, it ranks from 0 to 14. Low numbers, 0 to 7, are acidic. 7 through 14 are the high numbers, and those are considered basic. But, David, what about the 7 in the middle? Well, the 7 both counts for acidic and basic. 7
is neutral. That is a neutral range. I think there's one chemical that is in the 7. I think it's water. Water, pure distilled water is 7, which is neutral. So usually in the pH, the more hydrogen ions, the more positive hydrogen ions there are, the more acidic it is. And the pH is it's essential to body and ocean chemistry. Okay, the last term that we will discuss is the universal indicator. So the universal indicator is, I think you've seen this before. This is in the book, the Big Book of Science Experiments. I leave the link below I leave the link in the description below. The pH scale, I think we can get this on the camera. The pH scale is like the universal indicator is like this. Red, it's a color changing scale to determine how acidic or basic something is. Just like the pH, it is measured from 0 to 14, and like I said, it lets you know how acidic or how basic something is by color. So usually, like I showed you in the book, the redder it is, the more acidic it is. If it's green, the more greener it is, the more neutral it is, around that 7. And the more purple it is, the more basic it is. And I think you've seen it before, they usually come in little paper strips. These are to test for pH in pool, and these are actually universal indicators. Well, one of them is one of the colors is pH. Like, do you see this row is pH, and if you see it says OK right there, where it's supposed to be good, like around the 7 range. So let's go. Now we're gonna actually go test the pH. Okay, so here I have my little universal indicator, and here is my pool. So the instructions say to dip it in for like 15 seconds, right?
I think.
Okay, so I'm just gonna dip it in and leave it for 15 seconds. Okay, 15 seconds are up, and as you see here, it changed colors. This orange is the pH. So let's go back inside and measure it. Okay, so we took in the pH of my pool, and this is this is starting to get a little red. It's between 6.2 and 6.8 pH. So that means this is slightly less acidic than it's supposed to be. Well, I think we covered all the key terms for today, so let's get on to experiment of the day. Okay everyone, this is experiment of the day. Today's experiment, like we said about acids and bases, it's called lemon chemistry. So what you'll need some fresh lemons, a knife, a small measuring cup, and a small measuring spoon. It has to be a tablespoon, and baking soda, some liquid dish soap, and a clear cup for the reaction. Okay, the first step is that we have to roll the lemons just to get the juice out of it. So I'm just gonna move everything over here. Okay, let's roll them just like it says to roll on a table like dough. So this just releases the juice inside the lemons. So when we cut it, it'll have a lot of juice inside. So this one. Okay, so now we need the small measuring cup and a knife. So gotta be careful. And then we just cut the lemon in half. So is that the sharp side? No, this is the sharp side. Now, which way is the sharp side?
It smells like lemons.
It does. Is this way the sharp side? Yeah, that's the sharp side. So just cut
smells
our
so
lemon
good.
open. Then we just squeeze out the juice. So, I don't think so. So maybe you're probably gonna have to remove the seeds as well. As you can see, since we rolled the lemon, it activated all the juice that was inside. So, okay, that's our lemon, and then let me just give this another quick roll. Cut the lemon open. Just want to cut my fingers. There we go. Pretty juicy inside. And then there we go. We got our lemons, and then we don't need the knife anymore. Okay, and then in our empty glass, we add 1 tablespoon of baking soda. So is this 1 tablespoon? That's about a tablespoon. Is it in the camera? Okay, so we just add 1 tablespoon. And then add 1 teaspoon of liquid dish soap. I'm gonna go get a teaspoon really quick. Okay, got the teaspoon. So we take 1 teaspoon of liquid dish soap. A little more. There we go, that's our teaspoon. And then we just pour it to the baking soda. And we can just stir it up a bit. So, okay, that is starting to look like baking soda and soap combined. Kind of looks like snow. Oh well, we can put that aside. Now for the reaction. I'm gonna try to get a close angle. So what will happen, what's supposed to happen is that when I pour the lemon juice inside, which is an acid, it'll react with the bases, which is baking soda and soap, and it should make like little bubbles and carbon dioxide. So let's see what happens. There we go, look at that. They are reacting to form some carbon dioxide, as you can see. Oh boy, this is getting full really fast. Oh boy, oh mackerel.
Put more in.
Okay, no, it's overflowing. It's overflowing. Now I could just put more in. You want me to put more in? Oh gosh.
I want to make a mess because I'm that type of person.
There we go. Oh gosh. So as you can see, the lemon juice is reacting a lot with the baking soda. So you might be wondering what is happening. The acid, which is our lemon juice, is reacting with our bases, which are the baking soda and the soap. When an acid and a base combine, they make bubbles and they form carbon dioxide gas. The liquid soap, when you add it to water, it makes bubbles and foam. So when you add the lemon juice and the baking soda to the soap, it forms bubbles and foam that erupt right out of the glass. So like I said, we covered all our key terms for today. And so our next class is going to be about chemical reaction. I'm excited for that one. So thank you for watching. Like, share, and subscribe. Get this video to the front page and I'll see you later. Hi everyone, welcome back to Dprieto TV and welcome to the new episode of Prietology. So as we learned last class, we learned about what acids and bases are, and we learned how they're related and how they are measured. This lesson is basically going to bring all the episodes that we've done together. So in the first episode we learned about the basics like states of matter and compounds and mixtures. The second episode we learned about the parts of atoms like protons, neutrons, electrons, molecules, ions. And last episode we learned about how acids and bases are related and what they are. This episode is going to bring together all of them and how they react with each other. So this episode, like I said last time, is about chemical reaction. And my things go boom. Hi boss, does that mean we get to blow things up today? Absolutely not, not in here. What about like dissolving or setting things on fire or exploding or lasering or whatever aim there is in chemicals? No, just no. Okay, how did you even get inside my home? You're supposed to be at the lab. Well, yeah, how did I get inside? Meh, I'll just leave you. But sorry boss. Okay, so as you see, today's our lesson is called Why Things Go Boom. So today's key terms, we only have 5 key terms today. We have chemical reaction, reactivity series, combustion, activation energy, and catalyst. So let's start with chemical reaction. Okay, so our first key term is chemical reaction. Chemical reactions are electron interchanges between molecules. So when you put two chemicals together, basically when they react, they're switching electrons between each other, filling up their shells. And there's 2 key types of reactions. There's oxidations, which are losses of electrons. So if a molecule loses an electron, and reduction, which is when a molecule gains an electron. And there's also 2 types of chemical reactions. There's endothermic and there's exothermic. Endothermic likes to suck up all the energy as like heat or light, and then exothermic likes to puke out energy as in like heat or light. So usually in chemical reactions, they have like special equations. Like up here, this is an example of a chemical equation. It has 2 hydrochloric acid molecules, 2 sodium molecules, and the arrow means that when you add those 2 together, they turn into 2 sodium chloride molecules and 2 hydrogen molecules. Okay, so the ingredients required to make a chemical reaction are called reactants. And then once that finishes, the results of the chemical reaction are called products. And then the speed at which it happens, like some reactions can happen very slowly, like when iron rusts, it happens very slowly, not like in an instant. Or sometimes they can go really fast, like when you put baking soda with vinegar, it goes super fast. That's called the rate of reaction. And the rate of reaction depends on concentration, pressure, temperature, and a bunch of other different factors. Okay, so our next term is reactivity series. Reactivity series is basically, it's a chart Here's a picture of the reactivity series. The reactivity series is basically a chart that tells you how violently a metal, any metal, will react with others. Not just any metals, the metals from the periodic table. So the more reactive the metal, the more readily it will lose its electrons. So, like I said, chemical reactions are just interchanges with electrons. So if it's more reactive, it's more likely to lose its electrons faster. And basically it lists them from top to bottom reactivity. So if you saw the picture, the most reactive is potassium and the least reactive is platinum. I think the order is, it's potassium, then sodium, then lithium, calcium, magnesium, aluminum, zinc, iron, tin, lead, copper, silver, gold, and then platinum at the bottom. So yeah, that's basically what the reactivity series is. Okay, so our next term is combustion. Combustion is the combination of the two types of chemical reactions we saw, the reduction and the oxidation. It's called redox. It's basically a fancy chemical name for burning. Combustion is basically a fancy chemical name for burning. And it's a type of chemical reaction when the fuel, which could be, it's not just fuel like lighter fuel, it could be wood or paper, anything that helps it keep going. It's when the fuel combines with the oxygen part of air. So like the oxygen molecules is basically when it does. So the fuel and the oxidant can react to make heat and light. So basically the results of redox, aka combustion, is heat and light. So always the products of this type of reaction it will always be oxidized, means they will have oxygen. So yeah, let's move on to the next term. Okay, so our next term is activation energy. Activation energy is the energy needed to start a chemical reaction. So an example of this is like if you're trying to start a fire and the wood is wet, it's harder to start the reaction because it's not dry and coarse. So the higher the activation energy needed to start a chemical reaction, the more energy is needed to start it. So before the compound's reactant reacts, the stable chemical bonds have to be broken with the activation energy. So if they're tighter bonds, you'll need more energy. If they're weaker bonds, you'll need less energy. So some sources of activation energy that probably occur in real life are heat. Like to start a fire, some people just rub wood together to start a fire. Light, you could use light from the sun and a magnifying glass to like set a piece of paper on fire, or a spark like in lighters. There's a little thing in here called piezoelectric. It's a little crystal, I think, of quartz. So when you when you click the button here, this button, it hammers right on top of the piezoelectric, and that creates some electric current. And the electric current goes to the gas tank, which makes the fire. So basically, the piezoelectric is the activation energy in a lighter. Okay, so this is our last term. Our last term is catalyst. A catalyst is a substance that makes a chemical reaction to go faster. So when you put a catalyst in a chemical reaction, it makes it go faster. And it also lowers the reaction's activation energy. So if you put it before, you'll need less energy to start the reaction. So like if you have some like damp wood, and then you need a lot of energy to get it starting. But if you put some dry wood on top of it, it'll help it go faster, and you'll need less energy. So since less energy is used to start the reaction with the catalyst, it can happen at lower temperatures. And some top catalysts I think you have in one of the top catalysts that chemists use, I think you have in your house, is graphite. This is a pencil. This contains graphite. Lead is not in pencils. Lead is very poisonous. This contains graphite. All pencils contain graphite. And also another common one is platinum. And enzymes are a catalyst in your body. Enzymes are in your saliva. They help break down food with chemical reactions, and basically enzymes are catalysts in your body. Well, I think we covered all the key terms today, so let's get on to experiment of the day. Okay everyone, this is experiment of the day. The experiment is called the release of gas. So what you need is some sodium bicarbonate, aka baking soda, some vinegar, some water, a clear glass, and a match. We don't have matches, but we have this toothpick, and hopefully it will work. Okay, so what you do, you have to fill the glass 1/3 full of water. That's about 1/3. Add a teaspoon of baking soda and a tiny little bit of vinegar, because you don't want to start a vinegar and baking soda reaction. So we add that to the water. Nothing has happened. And now open the vinegar and just add a little bit of vinegar. Here we have our match. Okay, so we're gonna add it and we should see a reaction. There we go. Now we light this match.
Use an actual match, people.
And it should go out. Boom. The match goes out. Let's try that one more time. It goes out. Okay, so some of you might be asking, what is happening? So the sodium bicarbonate, aka baking soda, is a compound of sodium, hydrogen, carbon, and oxygen. So the reaction between the sodium bicarbonate, aka the baking soda and vinegar, as we all know, is bubbles and foam and fizzing. So when they react, the reactants are the vinegar and baking soda, and the products is carbonic acid and carbon dioxide. So, and the carbon dioxide gas, as we all know, extinguishes flames. Here, the chemical formula is up here if you want it. Okay, so this is how our classes are going to work. Next class is our last episode of season 1. It's our last chemistry episode, episode 5. I'm going to leave it a surprise, so I don't know. I don't want to tell you guys about it. So, thank you for watching. Like, share, and subscribe. Get this video to the front page, and I'll see you later. Hi everyone, welcome back to Dprieto TV, and welcome to the last episode of season 1 of Prietology. This season we've been talking about chemistry, and if you remember last episode, we talked about chemical reactions and what they are, how they're measured, and basically how they are in real life and what their properties are. Today's lesson is going to take what we've all learned, including chemical reactions, and put them all together. Today's lesson is called Earthy Resources. Why this lesson? This Earthy Resources, if you see the key terms are the needs, the necessities for Earth's chemical reactions. So let's get started. So today we only have 6 key terms for our last episode. Our 6 key terms are air, seawater, rocks, metals, alloys, and fossil fuels. Without any of these, our planet would not be able to have life as we know it. So let's start with our first term, which is air. Air is a gas, as you all know. It surrounds the entire planet, making up our atmosphere, and without air, we wouldn't be able to breathe, and we would die and be frozen by the vacuum of space. Anyway, air is composed of four main gases. 78.08% of air is nitrogen. It's not oxygen, it's nitrogen actually. Most of air is nitrogen. 20.95% of air is oxygen, breathable oxygen that we need. 0.93%, not even 1%, is argon. Argon is a noble gas that usually is in some light bulbs or some of those like plasma balls that contains argon, which can make cool colors. We don't need argon to live. And a very tiny 0.038% is carbon dioxide. And you may be asking, why do we need carbon dioxide? It's bad for our bodies. Carbon dioxide is actually a necessity for life. I don't know if you heard this, but it's called the carbon cycle. It's a chemical cycle that happens on the planet that it starts with animals, and then it goes with like the sky, and then like plants and stuff. So yeah, that's basically what the carbon cycle is. And without the carbon cycle, we would not have life. So we need carbon dioxide. So a layer of the atmosphere, I think is called ozone. Ozone is not particularly air. Ozone is O3. You might know oxygen, our oxygen that we have in our world, as O2. Ozone is O3. You can't breathe ozone, but the ozone layer protects the planet from solar radiation. So like all the alphas and betas and gamma rays and anyway, all the radiation. So because the atmosphere and all the air is a mixture between different gases like nitrogen, oxygen, CO2, argon, the heat sinks to the ground evenly because of the mixture of gases. Okay, so our second term is seawater. Seawater is Well, basically ocean water, seawater. So it helps keep the Earth's temperature steady. So if there's like some Earth temperature differences, seawater is a major part in leveling them. Earth is 97% seawater. All seawater is undrinkable. So that's why we have such problems today of getting fresh water and why it's such a major world problem right now. So like I said, major world problem, seawater is a major world problem because it's undrinkable, because large concentrations of salt in the seawater can cause severe conditions or death to the human body. Seawater is usually filled with NaCl, which is sodium chloride. I don't know if you heard of that, but if you have heard of that, I'm pretty sure you know what it is. Sodium chloride is table salt. I'm pretty sure you guys have used salt before in your lives. So things in that are like, if you drop like something heavy in salt water, it's more likely to float than you drop it in fresh water because salt water has an increased density more than fresh water, and we'll talk about density next season. Okay, so our third term is rocks. Rocks are solid material that make up the Earth's crust. So what you're standing on is probably rock. I think 1,000 meters is rock. I don't know. I'm unsure about that number. Ores. I don't know if you've heard of ores, like diamond ore, iron ore, uranium ore. Uranium ores are rocks, basically, that have gems, minerals, metals. So basically that's the standard definition of ores. So rocks are made of fused together mineral grains that come with compounds. We learned about compounds a long time ago in the first episode. So basically rocks are compounds of different minerals fused together. And as you know, there are three types of rocks: sedimentary, metamorphic, and igneous. Sedimentary rocks are fused together sediments that come from like rivers or streams, so like they fuse together over time. Igneous are rocks fresh out of volcanoes, so like once the liquid rock cools down, it can make different rocks and minerals. And metamorphic comes with pressure. So as rocks get squeezed like under the ground because of so much pressure, over long periods of time they begin to morph, hence metamorphic. So yeah, that's basically what metamorphic is. Okay, so our fourth term is metals. Metals are materials found in ores, like I just told you. Metals are found in ores, which are rocks with minerals, gems, or metals. So the properties of the metals, so if it's like good at conducting electricity, if it's good at conducting heat, or if it's strong or if it's weak, they all depend on metallic bonding. We learned about metallic bonding in the second episode. You can check it out up here. And so usually most metals, like iron, they corrode by reacting with oxygen in the air. So like when it rusts, basically it's a chemical reaction, which we learned last class, when chemical reactions can either happen slow or fast. So the chemical reaction with iron and oxygen in the air happened very slowly, and so the iron rusts because of the oxygen. There are three main types of metals. There's three main types of metals. The first one is reactive. Those are metals that corrode very easily, like I just said. So some examples are copper, lead, zinc, and tin. Second is ferrous. Ferrous, which is mainly magnetic. Those are the mainly magnetic metals. So like cast iron, iron, cobalt, nickel, steel. And the last one is noble. They're very unreactive, which means they're bottom of the reactivity series, which we learned last class. And they're good at making dyes. So gold, silver, and platinum, those are all metals at the bottom of the reactivity series. Okay, so our fifth term is alloy. Alloys are man-made metals. An example of a man-made metal is steel. Steel is a combination of like, I think iron and, oh man, I'm forgetting the other one. Oh well, I know it's mostly iron and sometimes some chromium. So alloys are made by melting two metals and combining them. So like if you put iron and chromium together, you could get steel. And if you put more chromium, I think you would get some better, stronger steel. So that's what they use to make steel. They use chromium to make it like rustless or stronger. Alloys have a melting range. Instead of like a melting point, which is like 1 degree of where they would melt, alloys have a range of temperatures at which they would melt. They can also help give metals better properties. So like I said, in the case of steel, chromium helps give steel better properties. So like they can make them stronger and so they don't get stained, like stainless steel, so it doesn't rust. Okay, so we're on to the last term of this lesson and the last term of season 1 of Prietology. So our last term is fossil fuels. Fossil fuels are carbon compounds made where there is no oxygen in the ground. So they're carbon compounds buried where there's no oxygen. So mostly there are 3 main types. There's coal, oil, and natural gas. Coal is, it's a rock, and it's actually, hold on, let me think. It's a sedimentary rock. I have to check again. Oil is a little dark liquid. It's crude oil made by like decomposing fossils and plants. And natural gas usually comes from extracting crude oil. So when you what's the word? Refine, there you go, refine. When you refine crude oil, you get natural gas and petroleum. So when they react to make energy that's used for electricity, they react with oxygen in an exothermic reaction. We learned what exothermic reactions are. Those are reactions that give off stuff, not suck energy in. So they give off energy in the form of like heat or light or electricity. So burning them releases sulfur dioxide and carbon dioxide, which is obviously not good for the environment and for humans. So that's why we're trying to move on to clean energy sources like hydro, solar, wind, and geothermic instead of coal, oil, and natural gas. Well, I think we covered all the key terms for today. Truth is, I couldn't find a science experiment for today because our topic today was not super sciencey. It was just about the different things that make up the earth and stuff. So I guess we will have to end season 1 experiment list. So this concludes all the chemistry lessons for Prietology and season 1. There will be no more chemistry lessons for season 1. Our next topic is physics. And also, I will not be uploading videos June and maybe not July because of something our family has to do. It's not traveling because we're in the middle of a pandemic. And also just I want to take a break from making videos. So I'll start making videos sometime around maybe mid-July to early August. So thank you for watching. Like, share, and subscribe. Get this video to the front page and I'll see you later.